If we look at our chemical reaction of hydrogen plus iodine giving us hydrogen iodide, we can see that for every 1 mole of hydrogen and 1 mole of iodine, 2 moles of our hydrogen iodide are made. So what that means is that as our reaction progresses, our concentration for hydrogen and iodine will be changing at a different rate than that of the hydrogen iodide because 2 moles are produced. Because our instantaneous rate at any given point in time is the same for the whole reaction, we need to adjust our coefficients in order to account for our stoichiometry. So the equation that's given here is assuming that we have the reaction A with a coefficient of A plus B with a coefficient of lowercase b, producing products that are C and D. So we're monitoring. We know that A and B are reactants because there is a negative sign for A and B. We know C and D are products because there are positive signs. We're forming those. The lowercase a we use as a coefficient to help us maintain that rate to be the same for all of our reactants and products. So if we were going to write it for our hydrogen, we would say our rate is equal to negative change in concentration of hydrogen, and it would be 1 over 1, but that is the same thing, right? So, and then we would have negative change in concentration of our iodine over change in time. But for our hydrogen iodide, is going to be positive because it's the product, 1/2 the change in concentration. Let me move this down just a little bit. It's positive because it's a product, 1/2 the change in concentration of HI over the change in time. So if we look at hydrogen and find its instantaneous rate, if we're looking at 50 seconds, we're looking at the change in concentration. It's decreasing in concentration because it's being used up. We look at the time. So again, we're drawing that tangent to the curve. Our change in time is 40 seconds. We find that our rate for the hydrogen being used up is 0.007. Our units are molarity per second. If we look at HI, okay, at the same time point, and we're producing it, so it's positive 1/2. Take our change in concentration over the change in time, we end up with the exact same rate. Let's try an example. For the reaction given, we are given the I- changes in the first 10 seconds, and we want to calculate the average rate in that time frame, and also the change in our H+ concentration. So the information we're given is about I-. So let's calculate the rate for I-. I- is on the reactant side, so it's going to be negative. We've got a coefficient of 3, which means we need 1 over 3 times our change in I- concentration over change in time. So we are given that change in concentration. we want to do change is final minus initial. So our final concentration is 0.868 molar minus 1 molar divided by our change in time, which is 10 seconds. And it says in the first 10 seconds, so our initial time is 0 seconds. And we end up with a rate of 4.40 times 10 to the negative third molar over seconds, molarity over seconds. So now let's calculate it for our delta H plus. So let's set up our rate equation. Rate is equal to, find H plus. So it is also a reactant, so it's negative. Our coefficient is 2, so 1/2. The change in H plus concentration, remember the brackets stand for concentration, over change in time. Now we know the rate. We found the rate at 10 seconds for the first 10 seconds, so we can plug that in. And that is equal to negative 1/2 of our change in H plus concentration over change in time. Now we're going to solve for this quantity here. So we got to move the negative 1/2 to the other side, which means we're multiplying by a negative 2. So multiply by a negative 2 to get rid of the negative 1/2. That gives us our change in hydrogen concentration over time, which equals negative 8.80 times 10 to the negative third molarity per second. Okay, so this number here would be our rate for the change in H plus concentration. We're looking at the exact same reaction under the same conditions, but now we want to predict the rate of change for hydrogen peroxide and I3 minus during the first 10 seconds. Pause the video and determine your answer. So if we look at and write our rate equation, it's negative change in hydrogen peroxide. So it's negative because it's a reactant. We don't have any coefficients, so we don't have to worry about a fraction. And we know that the rate was negative the rate is positive 4.40 times 10 to the negative third molar per second equals our negative. We want to get the hydrogen peroxide by itself, so the negative sign has to move over. So the change in concentration is a negative 4.4 times 10 to the negative third molarity per second for hydrogen peroxide. Okay, how about our I3 minus? So our rate, now this is a product, so it's going to be positive, should be increasing with time. There are no coefficients. So our rate that we previously calculated in our example is 4.40 times 10 to the negative third molarity per second. We don't have to move any negative signs, so that is equal to the production of our I3 minus. So we have found our two rates. Our hydrogen peroxide is negative because it's a reactant. our I3 minus is positive because it is a product. In order to measure the reaction rate, we need to be able to measure the concentration of at least one component in our chemical reaction. So if we have a component that is colored, we can use something called spectrophotometry, which measures the amount of light of a particular wavelength absorbed by one component over time. We can also use something called polarimetry. So polarimetry is the degree of rotation of polarized light. That's another way that we can measure it. So some reactions happen slowly enough that we can periodically take out an aliquot, a small portion of the sample, and analyze it. Others happen pretty quickly, and so we want to measure the whole sample. In this particular example, we're taking light, we're passing it through a slit to get a focused beam of light that is split into different wavelengths. So that is what we call a monochromator. Splits it into the different wavelengths of light. You can think of it like a prism. We can pass a single wavelength of light through the sample and detect that how much is absorbed by the sample at the detector and monitor that over time. Now, newer equipment, actually the detector can detect all of the wavelengths simultaneously, so there's no need for a monochromator, but it does simplify so that we're looking at one particular wavelength. We can also use something called gas chromatography. And so gas chromatography, we take a small aliquot, so a small sample of the reaction. We put it into a heated injection port that turns it into a gas. We use a gas to push that sample through a very long column, and very long, like 30 meters long. Pushes it through that column. The more the sample likes the column, the longer it stays on. The less it likes the column, the faster that it comes off. And this is a good way to separate mixtures. And then it passes through a detector, which allows us to detect when that sample is coming off the column. The height or the area of the peak tells us the quantity of the sample that has passed through it. So these are just a couple different ways that we can monitor the kinetics of our reaction over time.